So let us start by introducing to deep learning by looking at some famous examples. So an example that you've probably seen is AlphaGo. AlphaGo is a deep learning system, a reinforcement learning system developed by Google DeepMind, which learns to play the game Go to a level where it can beat the grandmasters. And there is a new version of the game called AlphaGo Zero, and then Alpha Zero, which is completely rule-based. So you basically just specify the rules of the game, and the game learns to play to make the optimal moves by only playing against itself, so without any actual training data. Then another famous example, of course, is autonomous cars. Here you see a Waymo car. And here is another example.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
So these are audio tracks that are generated by WaveNet, a deep learning system which generates audio from text. And this is really a level of generated text that is hardly, if at all, differentiable from a truly humanly spoken text. Now another example, and this example is a few years old, so it's not really state of the art, but it's nevertheless interesting. This is an example where you basically generate text from images. So the inputs are images, the output is a text which is trying to describe the content of the image. And this is using recurrent neural networks. And you can see that in some cases the system really works extremely well. So for example, a person riding a motorcycle on a dirt road in the top left, or in the middle left, you see a group of young people playing a game of frisbee. So these are all very nice. And sometimes there are little mistakes. So second column, first row, 2 dogs playing in the grass. Well, there's 1 dog missing, or maybe a 4th dog missing, which is in the background, but otherwise it's a pretty good description. And then you have complete failures, like second row right, a refrigerator filled with lots of food and drinks. And these funny mistakes are quite typical of machine learning systems, I should say. So even in systems, in learning systems that end up doing better than humans, on average, on a given data set, you often have situations where the machine makes errors that look completely stupid from a human point of view, while in other situations it really outperforms humans in cases where for a human it's essentially not doable because the differences are so subtle. So after these examples, I want to start introducing into neural networks as a learning architecture for deep learning. And the multi-layer feed-forward neural network that we will start with is inspired by the human neuron, but really it's just an inspiration. So human neurons are extremely complex. There are thousands of different types of neurons with different functions that are just barely understood. Nevertheless, the idea is that a neuron receives inputs through the dendrites. These inputs are activations that come from other neurons. These inputs have different weights. So depending on the strength of the connection between the neurons, different inputs will be weighted differently, and some of them can be inhibitory as well. So some inputs can have a negative effect. These inputs are being summed up or integrated in the cell body of the neuron and are then leading to an activation of the output of the neuron if the aggregated or integrated input exceeds a certain threshold. So then this neuron spikes and sends a signal to the next neurons. In artificial neural networks, we turn this qualitative function into a very, very simple mathematical description and say there is an input vector denoted as x1 through xn here. And we weigh these inputs with weights w1 to wn, sum them up, put them through an activation function, which could be something like a step function or a sigmoid function, and output this to the output neuron. Now you see in this illustration there is an input that is constant 1, which is multiplied by a weight w0. So this is basically a constant offset which defines how much or how little do the remaining inputs need to add up to in order for this neuron to spike. Now, in general, we call this a bias node. So the corresponding weight is called B. And we denote all the other inputs, x1 through xn, as the actual inputs that are coming from other neurons. And we then write the output or activation function as this, sigma of the scalar product of the weight vector times the input vector plus the bias. And here the activation function sigma is really applied separately to every entry of this vector. So it's an entry-wise application of this function. There are many different choices of activation functions that we can make. So a simple choice would be the identity function. So in this case, we are not changing the summed input at all. We just sum up and output to the next layer. Obviously, this is only something that makes sense for one layer. If we just concatenate neurons with identity output functions, then in the end we are still only doing linear operations. So there's no point in doing multi-layer neural networks with identity outputs. Now, a set of activation functions that has been extremely common in the past is or was these logistic or tanh functions. So these sigmoid functions which smoothly increase from 0 to 1 or from -1 to 1. And they mainly switch around x equals 0. So these functions have fallen a little bit out of favor with deep learning. And the reason for that is that in deep networks, where you have a concatenation of many neurons with such activation functions, you can be in a situation where many of these neurons are parked in a range where the slope of the function is small, so at either large positive or large negative values. And that means this is a range where the gradient of these functions is very small. Now, if you want to train the parameters of neural networks, you usually use gradient-based learning. So you change the parameters along the direction of the gradient or the negative direction of the gradient. So you have to have a significant gradient signal. Now, if you concatenate many functions with a small gradient, then you will have a vanishing gradient in the end. So you have very little information left in which directions you want to change your parameters in order to train the neural network. So deep neural networks with logistic or tanh activation functions are generally hard to train because of vanishing gradients. A function that is used a lot when it comes to deep learning are these rectified linear functions or rectified linear units, ReLUs, or derivations of this concept. So in a rectified linear unit, you simply have a function which is the maximum of x and 0. So basically this is equal to 0 for negative inputs and it's equal to x for positive or non-negative inputs. And so this avoids the vanishing gradient problem whenever you are around 0 or in the positive range. Of course, you have actually 0 gradient for negative inputs, but if you have enough neurons, this is not an issue. Now, let's come to the simplest neural network, a single neuron. So that idea has been developed by Rosenblatt in 1957, and it's called a perceptron. A perceptron is a binary classifier. So it's a single neuron which has an input vector, a bias input, and sums up these weighted inputs, puts them through a step function, which is 1 if the summed up inputs are greater than 0 or 0 otherwise, and tries to learn to classify the inputs into two states, zeros or ones. So it's a two-state classifier. And it's easy to see that this is a classifier which can learn linear functions. So looking at logical functions, it can, for example, learn the AND and the OR function, because you can represent the zeros and the ones by a linear dividing surface, which is separating the inputs that lead to zeros and ones. But the XOR function cannot be linearly separated. You would need two separatrixes in order to classify the outputs of an XOR function correctly. So this single neuron is very limited. It can only do linear, it can only learn linear functions. Now, the logical next step is to take not a single neuron, but many neurons, and especially multiple layers. And that leads us to the idea of multi-layer perceptrons that have been used since the 1980s. So in a multi-layer perceptron, we have a sequence of neural networks. We call the inputs just an input vector, and then count every layer of neurons after that. So in this example, you have a 3-layered network. You call the output layer, the output neurons are part of the output layer. The hidden neurons are in the hidden layers. So here we have a 3-layered network with 2 hidden layers and 1 output layer. Neurons I and J here share a common weight, WJI. So that is, if you are neuron J, your input weight from neuron I. So what can we learn with such multi-layer neural network? There's a very important theorem called the universal representation theorem, and it's actually not a single theorem. There are many universal representation theorems, and they differ by the degree of universality, in the sense like how what type of neural networks they apply to and what type of activation functions they apply to. But the gist of it is as follows. So neural network with a single hidden layer, so that means a 2-layer network, 1 hidden layer, 1 output layer, can learn to represent any smooth function f with an arbitrary accuracy. So that means in practice we can make the prediction error on a bounded set of values smaller than a certain threshold that we define. So we can learn to represent any such smooth function to an arbitrary accuracy in the limit of enough hidden neurons. Yeah? So in other words, if we use enough neurons in the hidden layer, then we can approximate our functions arbitrarily well. However, the practical usefulness of this theorem or these universal representation theorems is quite limited, because it doesn't tell us anything about what is the algorithm that we should use in order to find the parameters of such a network. So even if we know such a network exists in principle, it doesn't mean that we can easily find it. And the second issue, and that's a very severe issue, although in principle a 2-layer network is sufficient to learn such functions with arbitrary accuracy, it can be that the number of hidden neurons we need to get a good accuracy is huge. So there are examples, and it's not difficult to come up with such examples, where the number of hidden neurons you need to reach a certain accuracy in predicting the output function is exponentially large in the size of the input. And in many such examples, it can also be shown that deep neural networks can represent the output functions with a fixed accuracy with a small and non-exponentially large number of hidden neurons. So you can be narrower if you're deeper. Okay, in the next step, I want to introduce how to train the weights of a multi-layer perceptron, so a feed-forward neural network. So how to train the weights. And so we go back to our diagram of a multi-layer perceptron. So we have inputs, hidden layers, and outputs. And we want to predict an output and compare to a set of output labels. So we are in the regime of supervised learning here. We have defined inputs, we have defined output labels, and we make predictions using a neural network, and we compare the predictions with the given labels. We compute a loss function, and now we want to minimize this loss function. In this example, the loss function is just the mean square error. So it's the sum over the differences of the prediction and the given label squared. How do we do this? So we want to learn the network parameters, theta. Theta is just a set of all weight matrices between all layers of the neural network. And we can do that by computing the derivatives of the loss function with respect to the activation of the neuron at the output layer first. And then we essentially use the chain rule of differentiation to backpropagate the derivatives through the network. So in this way, we can compute what is the effect of changing the weight in each hidden layer of the neural network on the output loss function. And we can then update the weights so as to reduce this loss function. The backpropagation algorithm is essentially just an automated way of applying the chain rule of differentiation for this task of training multi-layer neural networks. More generally speaking, such neural networks can be thought of computational graphs. So every node is such an artificial neuron, and every edge in the graph is a computation. For example, taking the inputs that are resulting from the outputs of the previous layer of neural networks, multiplying them with some weights, summing them up, putting them through an activation function, etc. But we can generalize this concept quite a lot. We can say, all right, every such computation, whether this is similar to an actual neural network or not, can be written as such a computational graph, where we have nodes that basically hold activations or variables, and we have computations on the edges. And if these computations are differentiable, we can always evaluate the networks forward and backward. And backward means we can backpropagate errors, and we can use this in order to adapt parameters in our computational graph. And in this setting, any computation that is comprised of differentiable operations can be seen as a deep neural network, or in other words, as something where we can use the backpropagation algorithm to find parameters, as long as we have formulated finding parameters as an optimization problem where we minimize a loss function. And this is really the strength of all these modern deep learning packages such as PyTorch, TensorFlow, and JAX, and many others. We basically write any sort of computation as such a computational graph that is differentiable, and therefore any computation can be seen as a parameter optimization problem and becomes a machine learning problem. So this is an incredibly powerful way of rewriting general computational problems as machine learning problems. So again, in all of these examples, we generally have a forward step where we do the forward propagation of the computational graph, and a backward step where we do a backpropagation of errors that we use in order to adapt the parameters. Now we need to speak about a very important training algorithm that is called stochastic gradient descent. Before, I have indicated that we change the parameters along the negative gradient. So we compute the gradient, perhaps we use the backpropagation algorithm in order to compute the gradient in hidden layers of the neural network, and then we change the parameters to minimize the loss function. So we go along the negative gradient of the loss function. Now, if we would use just normal gradient descent, that would take extremely long and it would be extremely prone to get stuck in minima of the loss function. But the loss functions that we typically optimize have this form that you see here. It is usually a sum over all data points where every data point contributes a term to the sum. For example, a squared error between the prediction and the label in supervised learning. And that means that the gradient of this function also has this form. It's basically just a long sum of gradients of the loss functions of every single data point. Now in stochastic gradient descent, we say, all right, this looks basically like an expectation value. So you have seen above that I have equipped these sums with a 1 over m. So that has two reasons. So one reason is that we just don't get very large numbers if we have large training data sets, but we basically have always the same order of magnitude in the loss values, independent of how large our training data set is. But the other reason is now you really see this is basically an expectation value. And every sample of our expectation value is a single data point. So now we can say, all right, if this is an expectation value, why don't we just use subsets of our training data, called mini batches, and sample the expectation value? So we take a subsample of our training data, such a mini batch, and compute the value of the loss and the value of the gradient for this subsample, for this mini batch. And what you see here is the estimate of the gradient from the mini batch. And then in the learning step, we update the parameters along this estimated gradient. So, of course, every single iteration of stochastic gradient descent is much faster than an iteration of normal gradient descent, because we have done much less work in computing the gradient. We have simply only done the work for a mini batch and not for the entire data set. So that is one advantage of stochastic gradient descent. The other advantage, which may seem as a disadvantage first, is that we make a little error in computing the gradient. Because it is a sample from the full data set, that gradient, that mini-batch gradient that we compute, has an error associated to it compared to computing the gradient for the full data set. But the effect of making such an error is that we have essentially noise on our gradients. So we have a little extra direction on the gradient direction that is a random direction. And how random it is depends on how small our mini batch is compared to the entire data set. And the benefit of making such an error, adding such a noise to the gradient vector, is that we are able to escape small local minima in the loss function. So if that error is not too large, so large that we essentially destroy the information in the gradient direction, then this error is actually useful. It can help us to converge better. So stochastic gradient descent is a very, very important ingredient in modern deep learning. Essentially, all modern deep learning settings are using some form of stochastic gradient descent. All right, so this is the end of this session. We have introduced into multi-layer perceptrons, also called dense feed-forward neural networks, and the basics of training them, computing the gradients using the backpropagation algorithm and using stochastic gradient descent to optimize their parameters, and multi-layer perceptrons and many, many other computations can be seen as computational graphs that allow us to represent computations in a very versatile way and to represent the problem of training parameters with data in a very general way.